So good evening, everyone, to our webinar this evening. This is the third in the series Nuclear Waste Online for 2022, February 2022. And I'm really excited about the panel that we have with us here this evening. Dr. Gordon Edwards, Dr. Frank von Hippel, and Dr. M.V. Romana. We've got an excellent evening ahead of us. I am going to do just a couple of points in advance, just to set the context for this series. So our context is that we're struggling with a stockpile in Canada of high-level radioactive waste, nuclear fuel waste, that has been accumulating over a period of decades. We now have close to 60,000 tons of high-level radioactive waste. This is just the fuel waste. That's not the numbers for all the other categories of waste that we have in Canada. And since 1977, since the 1970s, the nuclear industry has been developing plan after plan, approach after approach, all with the endpoint of burying the high-level radioactive waste that they've created. And we're at about round 5 on this, and the current proposal, the current plan is one being promoted by the Nuclear Waste Management Organization, which is a coalition or a consortium of the waste producers, the 3 provincial utilities. And they have, over the last 10 years, done a number of site investigations. They're now down to 2 areas, the Revel Lake area between Ignis and Dryden in northwestern Ontario, and the area of Teeswater in the municipality of South Bruce in southwestern Ontario. And I say this as context for this series because many join us for each session. And I think that we've been very challenged by both the long-term, the longevity of these wastes, and by the industry's repeated approaches of communities as potential future hosts for all of this waste. And I think this evening is to say, just if you thought it couldn't get worse, well, it can. This evening, we're going to look at the next generation, and the next generation of radioactive waste issues for Canada can include the reprocessing of fuel waste, which we're going to hear from Dr. Edwards on, and it can include the introduction of a next generation, so-called small modular reactors. And both of these new sets of issues, challenges, problems bring with them proliferation risks. And we're going to hear from Dr. Frank von Hippel about those risks. So I'm really pleased to welcome the panel and to welcome all of you, our participants this evening. And our first speaker is Dr. Gordon Edwards, and well known to many Canadians. Dr. Edwards is a Canadian scientist and a nuclear consultant. He's a mathematician, and he has a PhD in mathematics. He's written numerous articles and reports on radiation standards, radioactive waste, uranium mining, nuclear proliferation, and he's an invaluable resource person for civil society organizations, primarily in his role as president of the Canadian Coalition for Nuclear Responsibility. So I'm going to hand it over to you, Gordon. Thank you. Your mic is off and you need to share your slides.
Thank you very much. I'm going to begin by sharing my slides and carry it on from there. Let's get this going. Share. Okay. There. Okay. I don't know how I can get rid of the band at the top. I can't even see the top of my own slides. There's a band of stuff there. I'll move it out. Okay. So I want to talk, I've been asked to talk about what is reprocessing, why should it be banned? This is only one aspect of radioactive waste, but a very important one, because the radioactive waste contains not only radioactive poisons, which remain dangerous for a long time, but also some radioactive resources, which both the military and civilian aspects of nuclear power are interested in. I'm just going to give a little background on this. This is a model of the uranium atom. Uranium is a heavy metal that was discovered in 1789, and before 1939, it was really only used as a colorant for glass and pottery. Then an amazing discovery was made. It was discovered that, no, why is my slide not advancing? Okay, the mighty neutron was discovered in 1932, and by 1934, it was shown that these neutrons can act as projectiles to create new radioactive atoms. This is called neutron activation. Enrico Fermi created a host of new radioactive elements in his lab long before the discovery of fission. Now, here are two examples. Tritium, everybody's heard of tritium. It's really an activation product. It's created by an ordinary hydrogen atom absorbing neutrons and turning into a radioactive variety of hydrogen. Chemically, it behaves exactly like ordinary hydrogen. If you have H2O, it behaves just exactly like ordinary water, but the molecules themselves are now radioactive. Cobalt-60 is another example. The cobalt-59, which is not radioactive, a little impurity in the steel, gets converted into a very highly strong gamma emitter called cobalt-60. Now, in 1939, we really learned the uniqueness of uranium. It's the only naturally occurring material that can undergo a sustained nuclear chain reaction. That was discovered in 1939, right at the dawn of World War II. And hence, it's the only naturally occurring material that can be used as a nuclear explosive, as at Hiroshima, or as a fuel for a nuclear reactor. A complication, however, is that there are two varieties of uranium, one with less massive atoms, the other with more massive atoms, called uranium-235 and 238, and only the uranium-235 can undergo a chain reaction. So this makes it difficult for bomb makers, for would-be bomb makers. They want to get a chain reaction going, and here's what happens. When a neutron is fired at a uranium atom, instead of getting heavier, which is what the research is expected to see, it's actually split the atom into smaller pieces. And these are called fission products. They're extremely radioactive, millions of times more radioactive than uranium itself, and they constitute the bulk of the intense radioactivity in the high-level waste, the irradiated fuel. But it also gives off more neutrons when this happens, and that's what allows the multiplication of chain of fissions, which results in enormous energy being released. Now, in order to make a bomb, you have to enrich the uranium. You have to go from less than 1% uranium-235 as in natural uranium. So it's only 7 atoms out of 1,000 in nature that are uranium-235. That's way too little to make an explosion. So they have to enrich it, and they have to enrich it all the way up to about 90%, preferably, to make a bomb, although they can probably make do with something around more than 20%. So for this reason, civilian facilities are not allowed to use uranium that's enriched more than 20%. But we're pushing the envelope. The new small modular reactors want to go higher in fission content so that they can make the reactors themselves smaller. This is the size of one of the enrichment plants that was used. It's one of the largest structures on Earth, and it used as much energy as a large city just to separate the uranium-235 from the uranium-238. That's all this factory does. It simply concentrates the uranium-235. That will be done whether it's for civilian or military purposes, but for military purposes, it'll go right up to 90%. Now, when uranium is bombarded with neutrons, it turns out that two things happen. You do get nuclear fission, but you also get plutonium. You do get something heavier than uranium. And the creation of plutonium takes place when an atom of uranium-238 absorbs a neutron and is converted into an atom of plutonium-239. Now, plutonium-239, when it's created, it's not found in nature, but it has a half-life of 24,000 years. So it can be used for nuclear weapons now or thousands of years from now. So we're creating a repository of things that can be used in nuclear explosive materials. The two bombs that were made and used in 1945 against Japanese cities, incinerating cities of men, women, and children, were Fat Man, made of plutonium, and Little Boy, made of highly enriched uranium-235. And Canada played a role in supplying the uranium for these bombs and also for the Cold War buildup of tens of thousands of weapons that took place later. Now, the first reactor built in Canada, this is a bronze plaque that was at the Visitor Center at Chalk River, and it talks about the first reactor ever built in Canada called the ZEEP reactor. It also started up in 1945. It was authorized in Washington, D.C. in 1944 as part of the bomb program. And if you go down towards the bottom, it says the ZEEP reactor was really part of a project to produce plutonium for bombs. That was the purpose of the original reactors. They were built for really only one purpose, and that was to produce plutonium for bombs. Now, a CANDU fuel bundle looks solid, but radioactive materials inside the fission products can leak out through tiny pinholes and cracks. Severe fuel damage causes massive leaks. Fuel suffers corrosion, distortion, and embrittlement in the reactor. Embrittlement means that the steel is more easily cracked. And here's a dry storage cask. We've got 60 tons empty, the storage cask, 70 tons full. So it only has 10 tons of spent fuel in it, or used fuel. And yet the container is 6 times heavier than the contents. And they also is a safeguard seal at the top to ensure no theft of plutonium. There's enough plutonium in this particular cask to make 6 or 7 Nagasaki-sized bombs. And this is the problem with reprocessing. Reprocessing is an effort to get at the plutonium, to get the plutonium separated out from that spent fuel. That can be used for civilian purposes as fuel, or it can be used as bombs. And there's the danger. Now, these are hot cells at the Argonne National Laboratories. Each cell has 3-foot thick leaded glass windows and 2 remote manipulators, robotic arms. That something like that is going to have to be used just to package the spent fuel bundles before burying them, if they want to bury them in an underground repository. This is what the burial container looks like, and they have to cram those fuel bundles into those tight containers before putting them underground. And in the process of doing that, they can cause damage and cause, therefore, radioactive releases. But the nuclear industry very often would like to get the plutonium out of the spent fuel before burying it. Now, in New Brunswick, there are 2 new reactors planned. There's the Moltex SSR cooled with molten salt and the ARC 100 cooled with liquid sodium. And they both plan to recycle used CANDU fuel. They call it recycling, but it's actually only extracting less than 1%. That's the plutonium, and they want to use that plutonium as fuel for those reactors. The federal government has assured citizens that the high-level waste of these non-CANDU reactors will also go into the planned deep geological repository. Well, here are 4 examples of sodium-cooled reactors that have failed in the past. These are basically fiascos, each one of them, although you could regard them as experiments that just went wrong. Nevertheless, these molten salt reactors have not been successful for reasons which will be explained later on by Mr. Romana, no doubt, Dr. Romana. This diagram is one that was drawn by my friend Robert Del Tredici, and I told him that there was a kind of a radioactive firewall between the plutonium in the spent fuel and the bomb. And that firewall is the radioactivity. The radioactivity is so intense that it would kill anybody who tries to carry one of these fuel bundles. In fact, a fuel bundle, when it comes out of the reactor, could kill a human being in a matter of seconds because of the intense gamma radiation. So that wall of fire that separates the military use from the civilian use can be removed by building a reprocessing plant. The reprocessing plant allows you to separate the plutonium, and then the plutonium can either go out the front door for reactor fuel, or it can go out the back door for nuclear weapons. And there's the problem. This is how much plutonium is needed to destroy a city. This is a glass paperweight that was built to be the same size exactly as the plutonium bomb that destroyed the city of Nagasaki, the plutonium ball that was in that bomb. And even the H-bombs, the gigantic nuclear warheads that have megatons of explosive power, they have to have plutonium in them too. And so plutonium is a very important element. If we look at the CANDU used fuel that we have in place, even a few years ago when we only had 50,000 tons, there are about 200 tons of plutonium. Even after 96,000 years of storage, there would still be enough to build 2,000 Nagasaki-type bombs Today, you could build 32,000 Nagasaki type bombs from that plutonium. So here's the question. Do we want to, in Canada, allow that to be happening? It appears the government is willing to contemplate it. These are tanks for liquid high-level radioactive waste left over from reprocessing in Hanford, Washington, at a reprocessing site. And here's a reprocessing plant at Sellafield, UK. Effluents from this plant have made the Irish Sea one of the most radioactively contaminated bodies of water on Earth. And the cleanup costs for both these facilities are in excess of $100 billion Canadian equivalent. So it's a very, very expensive and difficult job. And, you know, we can't get rid of the radioactive waste. We can only move it from one place to another or repackage it. When you handle the plutonium, it's got to be done in a glove box because it's extremely toxic, even though it doesn't give off much penetrating radiation. Very difficult when it gets inside the body. It can do a lot of harm. I'm almost finished. The important facts that I'd like to call to your attention are from 1941 to 65, 2 decades, Canada sold all of its uranium for bombs. From 1947 to 1975, Canada sold plutonium from Chalk River for bombs. In 1974, India exploded its first bomb using plutonium from a Canadian reactor. In 1977, US President Jimmy Carter banned plutonium reprocessing in the USA. That same year, AECL pressured Ottawa to begin reprocessing here in Canada and was refused. And now NWMO and Atomic Energy of Canada Limited have always kept the reprocessing option open, as has the Canadian Nuclear Safety Commission. So it means that any willing host community that agrees to accept radioactive waste for burial might well become the site for a reprocessing plant. There is no guarantee that that will not happen. In the 1970s, there was a very significant public process in the States called the Gizmo hearings. It became very clear that reprocessing is not needed, extremely expensive, and does not simplify the waste problem, but complicates it. Major Royal Commission reports from England, the Flowers Report, from Canada, the Porter Commission, and from New Zealand strongly cautioned against reprocessing. And I'll pass it on now to Frank von Hippel. Thank you.
Okay.
Great. Thank you very, very much, Gordon. That was excellent. Our next speaker is Dr. Frank von Hippel. And Dr. von Hippel is a senior research physicist and professor of public and international affairs emeritus at Princeton's Program on Science and Global Security, which he co-founded. And Dr. von Hippel is currently working on technical research on the technical basis for ending the production of highly enriched uranium, the separation of plutonium, and national enrichment of uranium, as well as nuclear arms control and limitations on ballistic missile defense. So very laudable work, and we welcome you, Dr. von Hippel. Go ahead.
Thank you. I only have a small number of slides. Fortunately, Gordon has gone over a lot of this territory, so there will be a little bit of overlap. So in outline, two routes to the bomb, enrichment and reprocessing. There's no economic reason to reprocess. And then there is a phony spent fuel management argument for reprocessing. Those are the 3 points that I will be making. So is another way to say what Gordon has already said. So we have in natural uranium, we have 2 isotopes of uranium. The uranium-235, the chain reacting one, is only 0.7%. And if you want to make a bomb out of it, you have to separate it, and that's called uranium enrichment. The uranium-238 is the remainder, and it doesn't chain react, but if it absorbs a neutron, it will turn into plutonium-239, which is a chain reacting element. And in fact, these are literally the first 2, and still only 2 routes to the bomb. U-235 was used in the Hiroshima bomb, and plutonium was used in the Nagasaki bomb. So 32 countries have nuclear power plants at this point. Under the Non-Proliferation Treaty, all non-weapon states have a right to both enrich and separate plutonium from irradiated uranium in a reprocessing plant for non-weapons purposes. But of course, purposes can change and in fact have changed with countries like India acquiring reprocessing technology for so peaceful purposes. In fact, assisted, in the case of India, assisted by Canada and the United States under the Atoms for Peace program. But then they did use plutonium that was separated with the assistance of that program for launching their nuclear weapons program. So with regard to enrichment, which Canada doesn't do, Canada uses natural uranium fuel in its CANDU reactors. But most reactors in the world do use low enriched uranium, in which the U-235 concentration has been increased from 0.7% in natural uranium to about 5%. And 9 countries out of the 32 have enrichment plants. And of those 9, 3 are nuclear armed states, which supply not only themselves, but other countries with low enriched uranium: Russia, France, and China. And then there's a multinational, Urenco, which is owned by Germany, the Netherlands, and the United Kingdom, and also has a plant in the United States. The United States does not have an enrichment plant at this point. It depends on these other suppliers. And then there are 3 other countries which have plants with capacity so small that they can't even supply a single large power reactor. And those 3 countries are Brazil, Japan, and Iran. And the obvious question is what purpose do their enrichment programs serve? Brazil, at this point, is the enrichment program is run by the Navy, Brazil's Navy, and they are working on a nuclear submarine. Japan, I think, just wants to keep that option open. And Iran will, that there's a big debate about Iran. And there was at one point, Iran did have a weapons program. And right now we're trying to get back to a situation in which a stable situation with Iran, where we have assurances that they're not going to use their enrichment program for weapons. The U.S. has, as I mentioned, has a enrichment plant which is owned by Urenco, and it's in New Mexico. So from my perspective, the optimal non-proliferation solution is not for each country to acquire its own enrichment plant, but to have a few multinational enrichment companies like Urenco. And I've been urging that solution on Iran, and in the hopes that we wouldn't get a competition of starting with Saudi Arabia, maybe Egypt, maybe Turkey, of countries around the Middle East, who decide to have their own enrichment programs, and look at each other's enrichment programs as nuclear weapons options. Now, reprocessing is the main subject tonight, and 7 countries out of the the 32 countries which have nuclear power reactors, separate plutonium from power reactor fuel. 4 of them are nuclear armed states: China, France, India, Russia. UK is just it's finally shutting down its reprocessing plant, its last reprocessing plant this year. And then there's Japan again. The original motivation was a fear of uranium scarcity, but there is no uranium scarcity, and recycling plutonium to extend the fuel is very uneconomic. Making plutonium for the low, the standard, the most common reactors in the world, the so-called light water reactors, making it with recycled plutonium costs 10 times as much as making that fuel with low enriched uranium. So you really have to go into the story of each country to try to understand why it persists. The original motivation was an expectation that global nuclear capacity would be much larger than it turned out to be. I mean, I show here the IEA projections in 1975. They showed that by 2000, there would be 2,000 large nuclear power plants in the world, and most of those would be breeder reactors, which would be fueled by uranium-238 instead of U-235, by converting that U-238 into plutonium. Well, in fact, global nuclear capacity plateaued, and even the IAEA, which likes high projections, doesn't think much will change. That this big increase will resume. So let me just. This just shows the price of uranium in constant dollars. And you can see that although the price of nuclear reactors has gone up tremendously, the price of uranium has not. There have been ups and downs. The ups when people were euphoric that there was going to be a nuclear renaissance, or that original projection of huge growth by year 2000. And then the downs have tended to be associated with nuclear power reactor accidents. At the average price of about $100 per kilogram of natural uranium, the cost of uranium contributes about 1/4 cent to the cost of nuclear power from a light water reactor. And that cost, the total cost of power from light water reactor is for a new one is about 10 cents a kilowatt hour or more. So it's not saving uranium by recycling plutonium would actually make nuclear power more costly, and it's already having a trouble surviving, rather than less costly. Now, we are hearing the song now that in fact a different song, a different motivation for reprocessing, that reprocessing can solve the spent fuel problem that you heard about at the beginning from Brennan. So the song is "Pay for my nuclear startup, and I'll solve your spent fuel problem. For my reactor, your spent fuel is a resource. What will be left after I take out the plutonium and fission it will be much easier to manage." And as you heard, Moltex and I gather also another company are singing that song in Canada, and we have companies in the United States which are singing that song as well. Now, that's not, it turns out that separating out the plutonium, not only, it does create a nuclear proliferation problem, but it does not reduce the radioactive waste problem significantly. And here I show a slide which sometimes induces laughter. What it is a calculation by the Swedish repository company, SKB, of what the doses would be to a farmer, subsistence farmer, living on the surface above a repository, their repository, which would be about 500 meters underground, and what the contributions to the dose that farmer got through drinking the water, and watering the plants and eating, maybe eating meat from cattle that were fed hay and drank water, this contaminated water, what the different contributions would be. And if you look at this, you see that and this is not just SKB, the Swedish company that has arrived here. There's a long time ago, in 1996, the National Academy of Sciences came to a similar conclusion, but it didn't have as photogenic a figure as this one. And you see that in the period out to tens of thousands of years or so, carbon-14 would dominate the dose. Carbon-14 actually made by neutrons captured by nitrogen entrapped in the fuel. Nothing to do with the fission process. And then in the longer term, out to hundreds of thousands of years, you would have a fission product, a long-lived fission product, iodine-129, which has a 17 million year half-life, much longer than plutonium. And by the way, these two reprocessing plants basically dump these two radioisotopes into the environment. The carbon-14 is released into the atmosphere, and the iodine in France and planned in Japan is just dumped into the ocean. And then finally, in the long term, coming up to compete with the iodine-129 is radium. And this actually gives some perspective, I think, to this whole subject, because the radium is from uranium-238, residual uranium-238 in the spent fuel. This is uranium-238 that was originally in a uranium deposit that was mined. So we would be exposed to this hazard even if there were no nuclear power. And in fact, we are exposed to radon, which is the decay product of radium. And people with basements like I have are exposed to this, and this is a significant part of the radiation dose we get from the environment. Now, finally, there's a curve here about an order of about a factor of 10 or so, or below the dominant radioisotopes, that's labeled plutonium-239. And plutonium-239 is highly toxic if inhaled. Last week I testified on behalf of some veterans who were inhaled plutonium during a cleanup from a nuclear weapon accident. But it is relatively insoluble, and so would move relatively small amounts would move up to the surface, and then at the surface, plants don't reject it, and the human gut also rejects it by a large factor. And so that's why even though it is a major contributor to the long-term radioactivity of spent fuel, which is the nuclear industry is tirelessly shows us pictures of that, it is a relatively small contributor to the hazard from spent fuel, and therefore removing it would not reduce the hazard from the radioactivity in the spent fuel very much, but it would actually make that radioactivity into a liquid form, which would then have to be solidified to be disposable, like the spent fuel already is. So I think that's all I have. Yeah, that's it. So I'll unshare.
Much. That was very, very helpful. Our next speaker is Dr. M.V. Ramana. And Dr. Ramana is a professor and Simons Chair in Disarmament, Global and Human Security at the School of Public Policy and Global Affairs at the University of British Columbia. He's also the director of the Liu Institute for Global Issues and the acting director of the Center for India and South Asia Research in the Institute of Asian Research. And his research interests are in the broad areas of international security and energy supply, with a particular focus on topics related to nuclear energy and fissile materials that can be used to make nuclear weapons. And Dr. Ramana is a very helpful resource for us on small modular reactors, and that's his topic this evening. Dr. Ramana, thank you.
Thank you very much, Brennan. Thank you all for tuning in today. I'm going to, Gordon and Frank have already covered a lot of the basic ground. I'm going to talk a little bit about this new generation of nuclear power plants that are supposed to fix all of the problems with nuclear power and slice your bread while it's at it. So, you must be sort of all familiar with this because there's been a lot of media hype about these so-called small modular reactors. There's been a lot of government support for it, especially here in Canada, and it's starting with the 2018 federal funding for the small modular reactor roadmap, followed by the 2020 release of the action plan by the Minister for Natural Resources. And as you know, there's been both federal and provincial level funding for different SMR projects and designs. And you may have also heard about the December 2021 announcement by Ontario Power Generation picking one particular SMR design from GE Hitachi. So I'll start by, just sort of very briefly saying what small modular reactors are. The definition of in the term small modular reactors, there are two terms which need to be defined. One is small, and small just means that it generates less than 300 megawatts of electricity. Okay, it could be much smaller, but by definition, that's what it has to be. The small does not mean that it needs to be physically small. So the graph below shows one dimension of the object, which is the height of the largest pressure vessel. And you see that that ranges quite a bit between some reactors. Small modular reactors are physically small ones, and some are really big. So one shouldn't be confused by the term small to assume that they're sort of nice and cute little things that you can put in your backyard. The other word that is involved in this term is the word modular. And the idea is that in the past, nuclear power plant construction has been plagued by problems that occur at the construction site. There are time overruns, there are cost overruns, and the hope for the nuclear industry is that somehow this can be avoided if all of the parts of the nuclear plant are built in factories, and these are called modules, and then at the site where the nuclear plant is being built, all that would have to be done is assembly. So it's sort of like Lego blocks. And I used to say this for a long time. And then last week, the French Atomic Energy Commission released a video about their SMR design, where this person, the head of the CEA, actually uses Lego blocks to show his nuclear reactor design. So I think that's a very good illustration of what they're being talked about. But you know, the problem, I'll just say, we're not going to go into this in any great detail, except to say that this idea has been tried. In fact, all construction that we know generally happens in a modular way today. We don't build houses by sort of baking bricks on the site or cutting down wood on the site. Everything comes prepackaged. And the same thing has been happening in the nuclear industry. And the experience that we had with modular construction in the nuclear industry have also been pretty dismal, especially in the so-called AP1000 reactors being built in the state of Georgia in the United States. Anyway, so all that is to say that SMRs are not going to fix the problems of nuclear power, but my job here is to talk specifically about nuclear waste. Gordon has sort of already talked about some of these designs, but I'll just very briefly say that there are 3 designs which seem to be actively under consideration. Till December, it used to be 5 designs because OPG, Ontario Power Generation, had 3 possible reactors they were considering. In December, they narrowed that down to 1, which is the BWRX-300 light water reactor from GE Hitachi. And there are 2 in the province of New Brunswick, ARC-100 and Moltex. And the only thing you need to sort of remember here in terms of thinking about radioactive waste is that these are all very different designs from traditional CANDU reactors that have been built in Canada. And this is going to have implications for how we deal with the waste that these produce. Okay? I mean, Gordon has already talked about ARC-100. I'll just say that it's a fast neutron reactor, which means that it uses molten sodium as the coolant, and also it uses enriched uranium fuel. So none of this has actually been done in Canada so far. We don't have any enrichment here, so this will require fuel to be imported, presumably from the United States or some other place. It also uses a kind of fuel which actually has been difficult to use in any commercial reactor because it swells upon irradiation. And so there's some basic problems with this design. The other design, Moltex, is sort of even more preliminary compared to the ARC-100. The ARC-100 is based on a design that we've known a lot about, that is running in Argonne National Laboratory, designed by Argonne National Laboratory. Moltex, on the other hand, is a very experimental design. It's really basically a paper design or a PowerPoint design, as they sometimes like to call it. It's sort of a variant of an old idea where the reactor is operated using nuclear fuel that is dissolved in molten salts, and also molten salts are used for cooling. But in Moltex, they try to put the salt inside what they call vented fuel tubes. There is no experience whatsoever with such reactors. The materials that would be required would be very difficult. And if you look at the various publications that are coming out of Moltex, they seem to be reporting different details. So I'm not even sure I know exactly what the design is. And in fact, I might even be bold enough to say the Moltex proprietors themselves might not know all about it, because the design is still under development at this point. But the most important thing about Moltex is also, in terms of the waste discussion, is something that Gordon touched about, which is that it has to use reprocessing. And in this particular case, they use a variant of what's called pyroprocessing, which they have this fancy name with funny capitalizations and so on, called WATS, which is a variant of a method that has been used in Argonne National Laboratory and has been quite problematic in terms of trying to deal with some of the spent fuel in the United States. And there are the only studies of this are at the theoretical or laboratory scale, and there are problems with scaling this up for commercial use. So, but the point is that this is also going to be a source of production of radioactive wastes. Because anytime you're dealing with any kind of radioactive materials, you might want to take away some material like the plutonium, but all of the other radioactive materials which are there are going to be there. There's no way to kill radioactivity, as it were, unless you're going to activate it with neutrons and things of that sort, and transmute them. And that's not what is happening here. Any chemical process cannot kill radioactivity, so the radioactivity is going to be there. And so for this process will also produce streams of radioactive waste that will have to be managed. Gordon has already talked about some of the problems with sodium-cooled reactors. I won't talk about that. I'll just say that the one experience we've had with a molten salt reactor is in Oak Ridge National Laboratory, again in the United States, where one reactor operated intermittently from 1965 to 1969. Its operations were interrupted about 225 times due to all kinds of problems, of which only 58 of them were planned. The others were unplanned. So it's not a very reliable design to start with. But again, for the purposes of this discussion, what is important to note is that that little reactor, which is just 8 megawatts of thermal power, has produced waste that have cost about $10 million a year for many, many, many years to deal with. And it's been extremely difficult to manage. Okay. And in general, I sort of want to come to the general point, which is that any nuclear plant in general will produce multiple streams of waste, multiple types of waste. You can't just put them all into one box. Each of them require different kinds of treatment. And in general, if you want to think about a smaller reactors, the per unit of electricity produced or energy produced amount of waste typically will be more, not less. And this is because a smaller reactor typically is less efficient at using neutrons, so more neutrons are going to escape from the core. That means that there's going to be requirement for more fuel, all else being equal, and also more activation of different things. So in this graph, for example, you see different kinds of radioactive materials that are being produced. Therefore, very different reactors from what we have. Unfortunately, I haven't had the time to do calculations, nor do I think it's possible for us to do calculations in the case of things like Moltex, because they just don't have a design out there. And anytime you ask them any question, they will say, this is confidential, is commercial proprietary information, we cannot share it with anybody. So nobody can really do an independent assessment of that. But to the extent that people have done these kind of calculations, what they find is that it's going to have more volume of different kinds of waste. And in a way that contradicts what New Brunswick Power has been saying, that it's going to produce less waste. And that's because they probably count it in a very different way. Okay? The other thing to note is that compared to, I mentioned that these reactors are different from CANDU reactors. And that means that, and that is one of the differences is that the fuel here has higher fissile content, certain kinds of materials, and therefore there are implications of this kind of use of spent fuel for what kind of repository is being designed. There are, for example, considerations that what you store underground should not become critical, leading to a spontaneous nuclear reaction. And therefore, the exact design that's used to bury, that is being planned for use to bury CANDU reactor waste will not work for these. So NWMO or AECL or somebody will have to come up with new designs for the repository. And that's not been done so far. Moltex 2, again, there has sort of multiple streams. I'm not sort of going to go into this detail, but just to say the same point, that there are multiple streams of waste that will be producing. And when they say, oh, Moltex produces less waste, they're only talking about one particular stream. Not all of it, and they assume all kinds of things about how efficient their processes are. The basic challenge here is that in the case of ARC 100 and Moltex, they produce wastes that are in chemical forms that are very difficult to deal with. It's not the radioactivity problem, it's the problem that you have things like sodium, which is, as many people might know from high school chemistry, does not react very well with water or with air. And so you don't want the sodium to be underground there. Likewise, in the case of molten salt reactors, the DOE, for example, found that they could not dispose of fluoride salts of uranium that were used in the molten salt reactor experiment in Oak Ridge in geological repository. So they have to do chemical processes to first separate out these things, and those things are expensive and difficult. Oops. I'll just say, so just to move away from the technical things, let me just say one word about the fact that in Canada, especially, small modular reactors are promoted as being suitable for producing power for remote mines and communities, which are off-grid, right? And this is not, this is promoted as a new application of nuclear power, but in actuality, this has been an old dream. And in the early decades of the nuclear era, there was a lot of effort to develop small reactors for remote areas. And the most investment and experience was actually with the US military. And the US Air Force tried to develop a molten salt reactor for a nuclear powered plane. The Navy and the Army also had their efforts. And one of them is a useful example to think about when we think about one of these reactors being built somewhere in the Yukon or someplace like that, which was the experience of a nuclear reactor built in the McMurdo station in Antarctica, PM3A, which was a huge problem. It's developed a lot of leaks, it cracks, and basically leaked out a bunch of radioactive material that the Navy started calling it Nuki poo. After the sort of obvious meaning. And eventually about 14,400 tons of the soil had to be removed and shipped all the way from Antarctica to a naval base north of Los Angeles for disposal, right? So you can just imagine what is going to happen. In general, there is no, as long as there's no repository, if a community decides to build a nuclear plant, they are also in essence signing up to hold the waste right there for a very, very long period of time, decades, maybe centuries, right? And you want to think about how this is going to operate in one of these remote communities. Okay, so let me sort of end here by just saying, to borrow a line from George Orwell's Animal Farm and twist it a little bit to say that all radioactive wastes are problematic, but some radioactive wastes are more problematic than others. And in the case of small modular reactors, all else being equal, and all else is not always equal, I sort of explained that. But I'll just say, if you're comparing two kinds of reactors and one is smaller than the other, the smaller one will typically produce more waste than a large reactor on a per kilowatt hour basis. And two of the SMR designs that are being considered in Canada produce wastes in chemical forms that are more difficult to deal with. And I'm going to end with a question that I really don't know the answer. Maybe somebody else will be able to do justice to this, which is the Nuclear Waste Management Organization, which is, is supposedly in charge of dealing with all the radioactive waste, are they authorized to deal with new waste forms that are not part of the original fleet of CANDU reactors? I'll leave it to that question and stop sharing. Thank you very much. Brennan, you're muted.
Yeah, I got it. It's our motto in the world of Zoom. So thank you very much to all our panelists. Those were excellent presentations, and I see we've got a lot of questions queuing up. I'm just going to stop the recording and we'll move to the Q&A. I'm going to again stop the recording.